Hi class, welcome to your first video in chapter 2 talking about modeling with linear functions. What you'll notice when we start with chapter 2 is that I'll be doing for each section pretty much a video that gives us a real basic introduction that follows PowerPoint like this. And then what I'll do is I'll follow up each of my initial videos with the second video that shows you how to use technology to very easily answer a lot of the questions in your math lab homework. I'm going to show you how to use, throughout this chapter, how to use your graphing calculator a lot. And then I'm also going to show you how to use this program called StatCrunch. And StatCrunch is a great program, and it's built right into my math lab, so you don't need to download anything. Um, and that'll be my first follow-up video. I'll show you how to use that. Okay, so the first video we'll talk about is section 2.1, is using lines to model data. Okay, so we're going to start with an example here, all right? And what we want to talk about is using a graph to describe some type of authentic situation. So the Grand Canyon is a beautiful landmark. I've never been there, perhaps you have. Yet the difficulty of finding a parking spot can detract from visitors' enjoyments. If you're driving around looking for a parking spot, it's not too fun. So the number of Grand Canyon visitors are listed in the table for various years. So I want to describe the data with graphs. All right, so whenever you see a problem like this, first thing you're going to look at is what years you have. So I start in 1960, 70s, the 80s, 90s, 2000, 2010, and 2015. And then look at over here, I have the number of visitors in millions. So this 1.2 means there were 1.2 million visitors that year. And then you can see the general trend of visitors. 1.2, 2.3, 2.6, 3.8. It's going up. All right, so as the years increase, so do the number of visitors. All right, so I'm going to define two variables, and this way I define variables is going to be very common throughout the rest of the class. Not too often are we going to be doing X and Y anymore. We'll be doing two different types of variables. So let's let V be the number in millions of visitors in the year that is T years. Okay, notice how I've defined this new variable as T years since 1960. All right, so we can describe the data with a table of values the following. So I define this, number of years since 1960, that's my T variable. Well, you'll notice the first number is 0. Because if I go back and look at my table, the first year I have is 1960. That is 0 years since 1960. And the number of visitors in million, the V visitors, would be 1.2 million. The next number is 10. Well, that's because 1970 is 10 years since 1960. And so on, 20. 1980 is 20 years since 1960. And so on all the way down, and then their corresponding values. All right, so I have this nice, neat table here. This is common in modeling when you're given a year, okay? And the year here, instead of writing all these big numbers, 1960, 1970, we define it as T years since some starting value, all right? It doesn't always have to be the first year that you're given data, all right? We'll see in later examples that's not always the case, but this is very, very common. All right, next I want to plot my points or my values TV, data values shown in the table. All right, let the horizontal axis be the t-axis and the vertical axis be the v-axis. So this you have to think about as going back to independent and dependent variables, like which variable depends on the other. Well, I don't think the number of, or the year since 1960 depends on the visitors. I think the visitors depends on what year it is. So that means this is my independent variable or my x variable, and this is my dependent variable or my y. That's why I'm putting it as t comma v. So what I'm doing here is I'm just plotting the point. So I'm putting up the first quadrant of the Cartesian planes. I'm labeling the horizontal axis as years since 1960, and then the vertical axis as millions of visitors. All right, so you can see that these marks are 0.5 marks. So 0.5, 1, 1.5, 2, 2.5, 3, 3.5, and so on. And it looks like these are 2, 4, 6, 8, 10. So each tick mark represents 2 or 2 years since 1960. So 0, 1.2, 10, 2.3 million visitors, 20 years since 1960, 2.6, and so on. And you can see the general trend, all right? Look at the general trend of the number of visitors. Now notice that the general trend isn't a perfect straight line, like it goes It kind of zigzags a little, but the general trend is that is a linear path or a linear relationship. All right, so what we just created is what's called a scatter plot. So the graph of a plotted ordered pairs is called a scatter plot. The scatter plot should have scaling on both axes, like it does here, scatter plot axes, and labels indicating the variable names and the scales used. Years is my scales, millions of visitors is my other scale. All right, so that's just a scatter plot, just plotting the first, or the values of the two variables together as ordered pairs. All right, so what we saw here when I was hinting at is that there's approximately linear related. So we can sketch a line that comes close to or on the data points of the graph in the previous example. Since the points in the scatter plot lie close to or on a line, but not perfect, remember I said it doesn't perfectly linear, we can say that the relevant variables are approximately linear related. They're close to being a straight line, but they're not a perfect straight line. Thus, they are approximately linearly related. All right, so one possible line that comes closer onto the data values is this blue line right here. Notice how the blue line, as I go through and try to fit the data, it doesn't actually like touch really any of the lines, but it does a really, really good job like showing the trend of the data, just the general trend of it. All right, so this line here, I just drew right by hand through the data. In the next section, we'll talk about how you actually find the line, the best line. But you can also notice I can draw a few other lines that come close to the data points. So like the green one also goes through them, the blue is the other one, and the red. They're all pretty close. But in general, there's one that's better than the others. All right, and for now, we're just going to stick with a linear line that we draw and approximate. But in the later sections, as I said, I'll show you how to find like literally the best line that fits the data. All right, so a model here is a mathematical description of an authentic situation. So we can say the description models the situation. Like this blue line here, or let me go back to this one. This blue line models or describes mathematically the situation. And it's describing it as a linear increase. All right, so a linear model is a linear function or its graph, like that blue line that describes the relationship between two quantities of an authentic situation. So not only is this blue line a model, but because it's a straight line, it's a linear model. All right, so the next example. Let's use a linear model to make a prediction and an estimate. All right, so I'm going to use the linear model shown on the next slide. I'll show it in a second to predict how many visitors will there be in the year 2022. So it's a few years from now. How many visitors will we have in 2022? Like if you look back at this table, you know, we don't know how many visitors there are in 2022. We want to use the model or the trend to guess. And then the next thing I want to do is I want to use the linear model that I have to somehow estimate in what year there were 4 million visitors. Okay, so how many will there be in 2022 and when did we have 4 million visitors? Just to go back and look at the table, we see that we had 3.8 million in 1990, and then 10 years later in 2000, we had 4.8. So somewhere between 1990 and 2000, some year between there, there's going to have been 4 million visitors. It's our job to find them. Okay. So let's go back and let's do this one. All right. Find out how many visitors there were in 2022. All right, first off, remember how we defined the t variable? Excuse me. The t variables is years since 1960. All right, well, 2022 is 62 years, okay, from 1960. So our t variable is going to be 62. So to estimate the number of visitors, locate the point on the linear model where the t coordinate is 62. All right, let's see and verify that the corresponding v coordinate is about 5.8. So here was my blue model. Remember I said the tick marks represented 2 years? So I'm going to go out to 62, and then what I'm going to do is I'm going to go up until it hits my model. All right, there, that's the number of visitors we expect there to be in the year 2022. Well, how many visitors is that? We'll follow where the model leads us back to on the y-axis, well, V, the number of visitors, somewhere between 5.5 and 6, that looks to be about 5.8. All right, how do I get this one? All right, well, remember the next question was use a linear model to estimate in what year there were 4 million visitors. So now we're working backwards. Okay, so to find the year when there were 4 million visitors, locate the point on the linear model where the V coordinate is 4. So what I'm going to do is I'm going to start here, 4, and I'm going to go over, I want 4 million visitors. What year is that? Well, here's where it occurs on the model. I'm going to scroll down here, look down here. That looks to be between 2, 4, 6, 8, between 6 and 8. So between 36 and 38, that looks to be about 37. So 37 years since 1960. All right, so the t coordinate is about 37. So according to the linear model, there were 4 million visitors in, well, t is years since 1960. 1960 plus 37 gets me the year 1997. Okay. All right, so here's a warning, okay? We create a scatter plot of data to determine whether the relevant variables are approximately linearly related. If they are, we draw a line that comes close to or on the data points and use that line to make estimates and predictions. It is a common error, though, to try to find a line that contains the greatest number of data points. You don't want to do that. Our goal is to find a line that comes close to all the data points. So you want to try to fit the line that has the best trend through the data. Now let's do another one. All right, and this is going to be introducing the intercepts of a model and what we call model breakdown. All right, so the percentage of cell phone users who send or receive text messages multiple times per day are shown in the table for various age groups. So I have these age groups, 18 to 24, 25 to 34, 35 to 44, 45 to 54, 55 to 64. And what I'll use is I'll use the age that falls in between them to represent that group. So instead of for the age group to actually put a number to it, 18 to 24, I'll use the age 21. And then 25 to 34, I'll use 29.5, and so on, 39.5, 49.5, 59.5. All right, so this is the percentage of people in that age group who send and receive text messages multiple times per day. So you can see 18 to 24, 76% receive multiple text messages per day, and then it steadily falls. So I'm in this age group right here. All right, so 42% of people who are in my age group, 35 to 44, receive multiple text messages per day. Okay, so here's how we're going to set up the model. Let P be the percentage of cell phone users at age A who send and receive text messages multiple times per day. So I have P that represent the percentage, and A is the age at which they send text messages. So I think the percentage depends on the age group you're in. So A, this age group here will be my X variable, but I'll call it A, and the percentage will be the dependent variable, the Y, but I will call it P. So let's find a linear model that describes the relationship between A and P. All right, find the P-intercept, what does it mean in this situation, and find the A-intercept, what does it mean in this situation. Okay, so view the positions of the point in the scatter plot. So I'm going to make the scatter plot. So it appears that A and B are approximately linear related. So we're going to sketch a line that comes close to the data points. So here in black are the actual data points. So remember, the first value I had for A was 21.0 and the percentage was 76. So at roughly the age 21, go up, it was roughly 76% of people, right? You're going to plot the rest of the points. And then what we're going to do is we're going to draw this line that goes through, not exactly touching, but a line that does a pretty good job modeling the data points. When we do that, we see that the P-intercept, so where the line crosses the P-axis here, occurs and when years, how old the person is 0. So at 0 years, we're saying the percentage of people who send and receive text messages is 106%. I realize we'll think about that in a second. And then the A-intercept over here occurs at 71. So we're saying when people are 71 years old, they receive 0% of multiple text messages a day. All right, well, that seems a little weird. We'll talk about that. All right, so the P-intercept is 0, 106, or P is 106 when A, the age is 0. So according to this model, 106% of newborns who use cell phones send or receive multiple text messages multiple times, or receive text messages multiple times per day. Does that make any sense? Is a newborn getting text messages? All right, so our model here gives a false estimate for two reasons. Percentages cannot be larger than 100%, and newborns don't send and receive text messages. It doesn't make any sense. So our p-intercept here from our model, which is a good model, it goes through the points, does a bad job estimating it or giving information. Similarly with the a-intercept is 71, 0, or when p is equal to 0, so the percentage of send and receive cell phones equals 0, send and receive text messages, is 0 when the age of that person is 71. Well, according to the model, no 71-year-old cell phone users send or receive text messages multiple times per day. All right, this is just false. All right, my father-in-law is about that age. We send each other text messages quite often. So it's just a false statement. So a little research would show that 71-year-old cell phone users send or receive text messages multiple times per day. All right, so we just got two cases here of the intercepts of them not making sense. All right, this is due to two things we call interpolation and extrapolation. So for a situation that can be described by a model by using a function whose explanatory variable is x, okay, in this case we call the explanatory variable a, or age though. All right, we perform interpolation when we use a part of the model whose x coordinates are between the two x coordinates of the data points. So let me go back and show you what interpolation is. That's if I want to use data or make a prediction between here and here. So when you make a prediction somewhere in between two existing data points. And we perform extrapolation, right, when we use a part of the model whose x coordinates are not between the x coordinates of any 2 points. So extrapolation we use when we're using the model predict points that are not between any x points, or past the first one or past the last one. We use extrapolation. All right, so the way it works with interpolation and extrapolation, right? When you're using interpolation, you have more faith in your results. They make more sense. But when you're using extrapolation outside of your data points, you really don't have too much faith in your model, right? These linear models do a bad job predicting outside of between 2 points. So interpolation is good, extrapolation not so good. All right, so when a model gives a prediction that does not make sense, or an estimate that is not a good approximation, all right, like in those two intercept cases, we say model breakdown has occurred, right? Or the model has done a bad job predicting outside or extrapolation of data values. All right, so let's do a little bit of modifying the model. Additional research yields the data shown in the first and last rows of the table. So I'm going to go back. Sorry, I'm going back to here. And what I'm going to do is I'm going to add another age group here and talk about their percentage that send and receive text messages. And I'm going to add another age group here and talk about the percentage that send and receive text messages. All right, so children 3 years old and younger, here's some information. All right, do not send or receive text messages multiple times a day. So if you're younger than 3, you're not sending text messages. The percentage of cell phone users who send or receive text messages multiple times a day kind of levels off at 5% for users over 80 years. So once you get to 80 years, it just kind of levels off at 5%. And the age of the oldest cell phone user is 116 years. All right, so I'm adding an age group 12 to 17 and using the age between them to represent the group. That percentage is 75. And then another age group being the age of over 64, so I'll use 70, right? They have about 7% of people who are cell phone users. All right, so recall that P is the percentage of cell phone users at age A years who send or receive text messages multiple times per day. All right, taking into account the 3 assumptions, I'm going to add the new data point I got here, that first group, and then I'm going to add the last data point, okay? So you don't want to just fit this with a new linear line. So we notice that until age 3, nobody is sending or receiving text messages. And then after age 3, kids start getting their first cell phone, whatever. The age who send and receive text messages, the percentage of people who send and receive text messages kind of skyrockets, goes whoosh, catches up to get here. And then the trend goes down, 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 down until you get past 70. And then remember, it said it bottomed out at 5%. So then our graph, instead of continuing down into the negatives here, it bottoms out around 5% until we get to the age of the oldest cell phone user right here. And this blue line would be a better model, even though it's not a linear model, because it does a good job talking about all our assumptions or all the new data we were given that's relevant.